So hi, my name is Kamil Jarosz. I'm a PhD student at HGH University of Science and Technology. And today I have the pleasure to present to you our short paper entitled Increasing Data Availability and Fault Tolerance for Decentralized Collaborative Data Sharing Systems. Presentation will be divided into two parts. The first being the introduction. I will talk about what is a collaborative data sharing system and some background. And the second one being our proposal on how to improve high availability and fault tolerance in such systems. So first of all, nowadays there are more and more requirements for sharing large data sets on a global scale. This is especially evident in research when researchers want to collaborate and they need to exchange information between each other. And they use various tools for that. So let's talk about some features of some desired features of these tools. So obviously, the tool has to implement secure and simple data sharing, and some form of transparent data access. Like I could mount a virtual file system and use it as regular files. And these systems examples include Google Drive or Dropbox. Those are very basic systems with basic features. But for more advanced features like efficient data access, sharing large data volumes when we need to share data for computation, large volumes of binary data, where features such as caching or partitioning are not only desired but sometimes are necessary, that's problematic. We also have situations where organizations provide their own storage. So these systems tend to be distributed and not centralized. And examples of such projects that implement these features are ScienceMesh or OneData. But today we want to talk about one specific feature, namely high availability and fault tolerance in such collaborative environments. And this paper is based directly on OneData. So OneData defines something called global entity store. On the diagram here, we can see three organizations and three types of data that we store on each one. The first one being the data files. Those are the physical data we want to share with each other, like the binary data for computation. We have file metadata which describe this data. And on top of that, OneData defines something called entity data. And entity data is basically organizational structures consisting of users, groups, and datasets, which logically describe structures that we are working on. And this data is distributed. So each organization has its own entity data, its own users, its own groups, its own data sets. And the organizations, when they communicate with each other, they share this data, and the whole data, the whole distributed data between these organizations is called entity store. And in this presentation, in this publication, we are talking only about the entity data and how to improve fault tolerance and availability of such data. Okay, so the organizational structures consist of entities, and those entities might be users, groups, or datasets. So, for instance, we have here a graph of such entities. We have users, groups, and datasets, and these entities might have relations between them. So, for instance, when a user is a member of a group, it is indicated in OneData by having a relation between the user and the group, which is directed membership relation. And the groups may be members of another groups, creating also nested hierarchies. So that's the background, and based on that, we propose an architecture of a decentralized global entity store for collaborative data sharing systems, which aims at, first of all, increasing availability, improving fault tolerance, and allowing easy entity migration. And we achieved that by, first of all, introducing an idea of a peer set, which I will talk about in a minute, managing shared ledgers between these peer sets, and using consensus and atomic commitment protocols. This is an alternative to DHT or blockchain approaches, which are pretty common and popular nowadays. So we define a peer as a standalone service, which represents an organization. And we define a peer set as a group of peers, which the sole purpose is to collectively manage a set of entities. So now, instead of having entity data stored within one peer or one organization, we store it within a peer set consisting of multiple peers. And the peer set ensures data replication and synchronization between these peers within the peer set. And it introduces an idea of decentralized authority, where there's no central point, there's no decision-making point where we decide how we want to change the data, but instead we change the data collectively by all the peers inside the peer set. The idea of the peer set is to be lightweight and possible to create it ad hoc when we need it. So it's not a configuration thing that admins do in a system. A user, when he needs a peer set, should be able to create it of any number of peers. One peer might belong to any number of peer sets, and an important thing is that the peer set is a dynamic structure. So, for instance, in order to allow migrations, we have to allow the peer set to change. So, at any point in time, any peer might leave the peer set, or at any point in time, a new peer might join the peer set. So, within the peer set, we store entity data. So, those are the users, groups, and data sets. And here we have an example. So we have a shared ledger, which every peer has a copy of. It's replicated across all the peers. And the ledger itself contains history entries, which describe the entity data. So it's a bit like a blockchain, right? So we have a user and a group and a data set here. And it is represented by these 5 entries when we add each entity. And then we add the relation between the user and the group and the data set. So in order to synchronize the ledger between all peers inside the peer set, we use a consensus protocol, which the purpose is to just coordinate these peers to agree on a common state of the ledger, so that every peer knows what the state of the ledger is. And the consensus protocol has to be fault tolerant. Usually more than 50% of the peers is enough to ensure a change, right? Because there's no two subsets with more than 50% which do not overlap with each other. The consensus protocol has to support dynamic participants because peer sets are dynamic. And we plan to add additional validation of changes. So not only the consensus protocol ensures that each peer has the same state of the ledger, but it allows also for a kind of verification, so that there's no one peer who can add a change that others do not agree with. And examples of the existing consensus protocol include Paxos or Raft. So now we have a situation where we have 2 peer sets. The left peer set is based on 3 peers. The right peer set is based on 4 peers. And the left one defines a user, an entity, and the right one defines a group. And it's possible to create relations between the entities from different peer sets that we call here cross-peer set relations. And the problem with this relation is that it has to be added in both peer sets atomically. So the first peer set cannot have information about the relation, and the second one, not. And the second problem we have is that peer sets must discover each other globally and globally identify the entities when we reference the entity, right? Because relations are designed as two-way references. So the first first peer set has to refer to the second entity, and the second peer set has to refer to the first entity somehow. And consensus protocol works on a peer set level. So now we have two instances of the consensus protocol. And this consensus protocol ensures that we have the same state within a peer set, so that each peer has the same information about the user, and each peer from the second peer set has the same information about the group. But in order to synchronize and add two relations at the same time for each in each peer set, we have to use an atomic commitment protocol. And the problem with atomic commitment protocol we have here is that it should work between peer sets and not peers. So peer sets are abstract entities and not concrete servers. So the atomic commitment ensures that either all parties commit a change or none of them does. Here we have an example of ledgers from these peer sets, right? On peer set A, we have to add a entry about the relation from the user U2 to the group G2 from second peer set. And in the peer set B, we have to add this relation referencing the user from the first peer set. So we have actually two propositions here. The first one being an implementation based on generalized Paxos atomic commit, GPAC. That's an existing algorithm which combines together consensus and atomic commitment. And the second one being using an existing atomic commitment protocol, for instance, two-phase commit, along with special ledger entries. And these special ledger entries allow us to treat a peer set as a concrete entity because we can have a shared state within the peer set. So each peer set is treated as one party in the atomic commitment protocols in this case. The second problem that I mentioned was how to identify globally entities. So the problem is we have to somehow identify the group G2 inside peer set A and the user from peer set B, right? So we cannot use content addressing because content changes. We can't refer to peers directly. We can't refer to peer sets, right? Because peer set is an abstract entity. It doesn't have an IP address, for instance. But we also cannot refer to peers directly because peer sets might change, right? It might be different peers in a month from now. So that's not acceptable. And also we have no central authority. The whole system is decentralized. So our proposition includes creating a lightweight peer set identity management service called PIMS, which are solely responsible for keeping track of peers in peer sets. So they do not have any information about entities. They only know which peers are actually in peer sets currently. And the network of PIM sets is also decentralized. For instance, we have two PIM sets here in the green color here. And using such service allows us to reference other entities globally because now we can use address of the PIMS service and, for example, append a peer set name, unique peer set name. So we now have identified the peer set because the PIMS is a concrete service. We have its address and it knows which peers are currently inside the peer set. Appending a entity name, we can uniquely identify the entity. So a quick summary of the graphic before is that we have consensus and atomic commitment protocols which synchronize the data within all the peers in the system, and on top of that we have PIMSs which identify peers within all peer sets within the system. So the summary is that we propose a new architecture of a layer for one data, which consists of, first of all, peer sets with consensus-based decentralized collaboration, atomic commitment protocols, and the peer set identity management services for easy discovery and global entity identification. So in one sentence, our architecture ensures high availability and improves fault tolerance by introducing collective management and replication of entity data by autonomous organizations. And of course, that's just a description of an idea. So our future work is based on two things. The first one, implementing a prototypical implementation of the consensus and atomic commitment mechanisms and evaluating it. And it includes also the comparison of GPAC and our proposal of atomic commitment. And the second is implementation of a prototypical implementation, and evaluation of the global entity identification network with PIMSs. And yeah, that's all for me. So I guess that's time for questions.
Thank you very much. Are there any questions?
Maybe I'm awful.
I have some also, so go first.
Mm. So the first one is I didn't want to get why do you need both the consensus protocols as well as the commit protocols? So from my point of view, these two kind of protocols make the same problem. So why do you need both? Why don't you use just say commit?
Well, because when it comes to consensus, the idea of using consensus protocol is to improve high availability. So if one peer dies or is unavailable, the others might change the entities within them, right? So there's only at least 50% of the peers is enough to ensure a change, right? But atomic commitment needs all of the peers to commit that, right?
No, this is not true.
Okay.
Atomic commit, at least the classical versions, they can ensure tolerance to any level you want. So even if one node, if let's say one node or the nodes is alive, it can make decisions itself.
Well,
so this is not the reason.
Yeah, I mean, it depends on how you define it, but here the other thing is that when we talk about consistent atomic commitment, we have each peer set contains replicated data, and peer sets between distinct peer sets contain you could call it shards of data, right? So that's one of the generalized practice atomic commit. That's one of few solutions that we found which try to somehow connect these ideas. So replicating the data within two shards of the database, right, and synchronizing the shards with each other. So that's yeah.
Okay, we can later.
Yeah, sure.
I have one question. This architecture that you propose is for one data,
yes.
But can it can be generalized also to other solutions that you mentioned?
Yeah. So it's well, there's not much of solutions that use the features that we mentioned here. There's Science Mesh, but Science Mesh has it has so very basic features. So for example, Science Mesh doesn't implement groups yet, so we cannot group users and apply some shared policies, right? It has only features like sharing a link to the data or inviting someone. So one data. But we didn't find any other systems which we can apply this with. But the whole idea is inspired by one data, but it's not made specifically for one data. right? It has some general ideas here.
Mm-hmm. And you also mentioned that what you propose, the part of distribution is a bit alternative to the blockchain approach. If you could elaborate more on that, so what are the strong points in comparison to using blockchain?
Yeah, so the problem that we had with blockchain is that blockchain is a public network, and the organizational structures here, they are only shared with organizations that that are allowed, right? So there's no the entity data on this diagram here. It's not public. It's referenced only when an organization agrees on this. The part of the data is shared to another organization. So in blockchain, it would be difficult to implement that. It will be possible, but difficult. But here we have an easy implementation without the blockchain.
Okay. So the blocker was combining blockchain with security.
Yes. Yes.
Access control. And my last question: have you done any practical experimentations with the solution?
Yeah. So that's ongoing. We only described the idea as a short paper, and now we are doing implementation of the first prototype and evaluation.
Okay. Thank you very much.
Thank you.